Hello everyone, Dr. Chen here. We're going to study magnetic force in this video. So the magnetic force on a charged particle is a vector product, is a cross product between the velocity of the charged particle and the magnetic field. And then we know the velocity is a vector, B magnetic field is also a vector, two vector cross product give us magnetic force. And now if we didn't learn cross product, so let's try to interpret it in such a way. So the magnitude of the magnetic force, is proportional to the charge of the charged particle, the component of the velocity of the charged particle that is perpendicular to B, and the strength of the magnetic field. Now, V perp can also expressed as V sine phi, and phi is the angle between B and V. So we can calculate the magnitude of magnetic force using this equation, Q times V times B sine phi. Phi is the angle between V and B. Now apparently, if phi is 0, sine phi is 0, there is no magnetic force. So if the charged particle is moving with a velocity that is parallel to magnetic field, there is no magnetic force. So if V parallel with B give you phi equals 0, give you your force equals 0. Now, on the other hand, if your V is 0, apparently you will see, because F proportional to V always, your magnetic force is 0 too. If the translate into physical situation, if you have a charged particle at rest here, at rest in the magnetic field, there is no magnetic force at all. Even if the charged particle is moving, there has to be an angle, a not zero angle between the velocity and the magnetic field, so the magnetic force is not zero. Then how about the direction? Look at the picture, we find out V and B can determine a surface. Is this surface, and the magnetic force is perpendicular, both V and B is perpendicular to the surface made up by this V and B. And this is, we call it the right-hand rule for magnetic force. For a positive charge, if we want to find out what's the magnetic force on a moving charged particle, what do we need to do? First of all, we need to put our forefinger in the direction of velocity, then curve it into direction of B, then our thumb gives us the direction of magnetic force. Then we may ask, what about a negative charge? In previous slide, it gave us what's the direction of magnetic force on a positive charge moving. For a negative charge, so we follow the same procedure. We put our forefinger in the direction of V, curve it into B, then our thumb should point into this direction, right? Your thumb is going to point into this direction. This is our finger, or thumb pointing up. And then we choose the force on the negative charge is opposite direction of our thumb after we do the right-hand rule. Now remember, if you have positive charge, use the right-hand rule, you'll find out the magnetic force automatically. If it is a negative charge, use the right-hand rule. You find your sum give you the opposite direction of the magnetic force. And magnetic force is a granny TV or monitor we use. It's a very, very big and thick monitor. We use the physics principle behind that monitor or TV. We call it a cathode ray tube. So let's watch a video of demonstration of how electrons bend inside a magnetic field, which is also a demo we did in a class.
This is a cathode ray tube, which produces a beam of electrons. The beam is visible due to argon gas in the tube. The electrons here are moving so fast that gravity is negligible. Watch what happens when I bring a magnet near the beam. The beam deflects, which shows that there is a transverse force due to the magnet on the moving electrons. In general, any charged particle that is moving in a magnetic field will experience this fundamental magnetic force. The beam is horizontal outward. When the magnetic field points to the right, the beam bends downward. When we switch the magnetic field, switch the direction of the magnetic field, the beam bends upward. When the magnetic field is pointing straight down, the beam bends to the left. But it has to do that because we can get back to our original case by just rotating the magnetic field. That's where we started from, the beam bending downward. Finally, when the magnetic field and the beam are parallel, there's no deflection. There's no magnetic force. The fundamental magnetic force law quantitatively accounts for our observations. The force is the charge times the vector or cross product of the velocity and the magnetic field. The force is perpendicular to both the velocity and the magnetic field, and the direction is given by the right-hand rule. The force is a maximum when the velocity and magnetic field are perpendicular to each other, and it is zero when they are parallel.
Now we are ready for the following example. So we know the magnitude of magnetic field, which is 1.25 Tesla. And the charge is 8.5 microcoulomb, moving in the north with a velocity 4.75 km per second. It's deflected to the east, which means the force is pointing to the east. And we ask us what's the sign of the particle. So we need to use the right-hand rule, right? So we need to first use our forefingers in the direction of V, and then curve is the direction of B. So what's the direction of B? You see a dot. So it means it's pointing out of the screen. So for us, we need to use our forefingers in the direction of V, and then we curve them into the direction of B. Our sum should be pointing to the right, sum pointing in the same direction of force, which tells us this is a positive charge. And now it asks us what's the force? What is the force? So we use the equation we just learned. Force equals QVB sin phi, and phi is the angle between V and B. We find V pointing to the north and B pointing up, so it's perpendicular to V. Phi is 90 degrees. 8.5 10 6 coulomb. V 4.75 meter per second. E and sine 90 degrees, which really is just one. The unit is Newton. And then we put all the numbers, we find it is 0.0505 Newton. Now we find out the magnetic force is always perpendicular to V. So if we start with a charged particle moving perpendicular to the magnetic field, force perpendicular to V and perpendicular to B always. So from what we learned from uniform circular motion, the force is always perpendicular to V. The acceleration is going to be the same magnitude and always pointing to the same signal, so it's going to be a uniform circular motion for the charged particle. And for uniform circular motion, we are going to have a centripetal acceleration which equals mac, and AC centripetal acceleration is v squared over r, and this centripetal acceleration, the force, is provided by the magnetic force. The magnetic force has to be equal to centripetal acceleration from Newton's second law. So we have this equation. If we know the mass of the particle, we know the velocity, we know the charge, we know the magnetic field, we can find out the radius of this uniform circular motion. So let's do one example on this. So we have an electron from point A. Initially has a velocity pointing up and the magnitude 1.66, 10 to the 6 meter per second. Then we find out the trajectory of the electron. We want to find out the direction and the magnitude of the magnetic field. Okay, so direction of the magnetic field. Of course, force is pointing to this direction. If we use right-hand rule, we put our forefinger in the direction of V, and our thumb should point into this direction. You have your forefinger this way, thumb should point into the left. So you need to curve your forefinger to the magnetic field B and give me thumb to the left. So B is pointing into the screen. And why my thumb should point into the left? Because this is an electron, is a negative charge, so the magnetic force would be in the opposite direction of my thumb obtained from right-hand rule. Now the magnitude of B. So we know QVB sine 90 degree equals mv squared over r. Magnetic force is a centripetal force. Basically, that's how we get this equation. So B is, this is just the 1. So B is mv over Q times r, and m is the mass of the electron, 9.1 10 to the negative 31 kilogram. Velocity, charge of electron, and radius. Radius is 5 centimeters, so it's 0.05 meter. Everything together, we find the magnetic field is 2 times 10 to the negative 4 Tesla. So this is about magnetic force. I will see you in the next lecture. Thank you for watching.